The problem I posed is typical, you got the ball, goes off the ramp, falls to the floor. The range of the ball is 30 centimeters. The ramp slope is 0.2. Vertical drop is 1 meter. Want to find the velocity at the end of the ramp. We don't care what happened between release or whatever happened on the ramp. All we're interested in is finding the velocity at the end of the ramp from the projectile motion. Don't assume horizontal initial velocity, which I allowed you to do on the lab because it's not going to make much difference. At this slope, it would make a difference. Okay, then design your solution using symbols and execute it. Most people are off to a pretty good start, but I would recommend that you do this and write the forward equation. You write the forward equation, uniform accelerated motion in the x direction, and I'd write out the full equation. And then I would start working my information into those equations. This is a tough problem, but getting it set up shouldn't be tough because you should automatically do this every time you see the equations, every time you see the thing. If you have to rederive the equations of motion, go ahead. You get tired of rederiving it. So I'm going to pause the video. Now you get tired of rederiving those equations and you'll memorize them. Okay. Now, some of you still don't have the equations down, some do. And this indicates to me you don't all know the equations like you really need to at this point. Because those equations are not going to be provided for you on the test. You don't know the equations anywhere. You find them wiped off there. Okay. Some of you do. Now, if you want to get the equations, this picture can be very useful. V naught, VF, V average, and delta T. Then average acceleration, which is just the acceleration. If it's if acceleration is uniform, this is a straight line. So the average acceleration is the rate of change of velocity, which equals delta V over delta T, which is VF minus V naught over delta T. So we can translate that to well, solve that for VF, you get V naught plus A delta T, which is exactly what you get if you integrate twice. Yeah, just once, actually. Just integrate acceleration equals A. So you do that by an integral, which is even simpler than this. You have to know that. Okay, I'm going to have a test in a couple of weeks. And I will ask you to drive during the night. You have to know the structure in order to be able to think through the problems. Not just pull out equations that seem to work, but equations that you know work because you know how they're derived. And you can always check the equations. You never have to memorize them, although if you use them a lot, you will. And probably a good idea to go ahead and memorize them, even if you know how to derive them. You've always got the backup of derivation. I showed you how to do that in the first step with calculus, and I showed you this in like the first step. You should be able to do it both ways. And then you can figure out which way is simpler and which way you want to use in which situation. And one thing I'm emphasizing is that AI will solve that problem for you. But if you don't understand the physics by understanding what I'm trying to get you to understand, at least as deeply as you can, you're not going to know what to ask AI to do, except something that any idiot could ask it to do. And why ain't anybody going to pay you to do it? Okay. So at least be a useful idiot, which is something I keep striving for. Okay. Personally, we're all idiots. Compared to what AI is going to be in the future. Okay. And then pretty much compared to what AI already is. If you're going to live with it, you got to know what to ask it to do. And you won't know what to ask it to do unless you know some physics and you know some engineering. I'm reading a science fiction novel right now. For the last year, I've been reading mostly 19th century novels. Okay, because I love the language, love the way they use the language. The really great uh, authors. Then I saw this science fiction novel. And what I read last night was something that eventually I'm going to probably share with you. Because it's this guy who, along with 12 other guys, is being blasted into orbit in a way as to avoid this potentially hostile 3-mile diameter alien ship. Okay. So they're using ICBMs, ballistic missile launchers. And this is like 3,000 years in the future. Society hasn't progressed beyond that. In 3,000 years, it keeps progressing and falling back, progressing and falling back. And that's kind of interesting. But the description of being blasted into orbit and what it took to be able to blast one person at the nose of this thing with just a protective shield and all the ions coming within inches of the body. And the absolute terror of the whole thing, even though the guy knows all kinds of cosmology, you can figure out orbital planes, the whole business. Pretty amazing. So I'll try to find a way to share that with you. I'm not sure why I mentioned that right now, but it kind of blew me away. The night before, something blew me away. Good novel. All comes back to this. All comes back to the definition of rate of change. So anyhow, you get this equation. So you could write, if you prefer to use just v, so you have this as v of the function of t, not the final velocity on an interval. You have your choice. Okay. You write vf equals v naught plus a delta t, or v equals v naught plus a t. Then you have another equation that you can easily get that in general, delta S, which is your displacement, okay? Now, if delta X is delta X, which it will be for X, and I better put subscripts X on here. This is Vx, this is A sub X. T is the same, both sides. Okay. Okay, if I write this equation, then I could write I'm going to write delta x. Where delta x is x minus x naught. I just put a little note there. Okay. I use a delta there because I don't want to include x naught. I could include x naught on this side. So x equals this plus x naught, your choice. Got a question. Stop. So the question was just, did you write delta x equals x minus x naught? Answer is yes. Can you read it from where you are? The answer is, not unless you got way better eyes than I got. Okay. But you should know. And you do because you asked, did it say what you thought it was going to say? Okay. And all I'm saying is, if you want to replace delta x by x minus x naught, or you want to move the x naught over onto this side, you can do that. But I think it's simpler if you notate it like this. So I'm not going to include that there because I don't want to mess up the whole thing. Now, the other comment was, well, can't we assume that the acceleration in the x direction is zero? Yeah, if you're assuming an ideal projectile, you do that. If it's not an ideal projectile, then this probably isn't a constant acceleration. So yes, for ideal projectile motion, it's always zero. We're going to write it out anyway because we need to write these equations out. We need to see how things are related. And in a minute, I'm going to do something with that AX. I'll put an arrow through it and write point to zero. So that that whole term there becomes zero and we have constant velocity. So since the question came up, yes, that's what we're going to do. I don't recommend doing it until you are completely sure that it's safe. Okay, it is, but don't take my word for it. Make sure you know in the depth of your understanding that it is so. Okay, and then we get two other equations, which is that okay. Now, in both of these cases, writing it again, delta x is x minus x naught. Okay. You can put the x naught over there if you want, your textbook does. Not necessarily a bad idea, but I want to think in terms of there are 5 quantities and only 5. I see, there's my hand from the camera. 5 quantities. That's a little scary. I don't want to do that again. 5 quantities. You have 4 equations, each with 3 unknowns. Each can be solved for the remaining. If you only know 3 things, you can find an equation that has those 3 things to be solved for 4. That's a scheme. Said it before. I'm not going to keep saying it. But you have to know that scheme. You have to understand that. Okay. Then it becomes very easy as long as you can identify what you know, which is a little tricky in this case. So I'm assuming you know all this. Okay. I'm thinking I'd rather not have to repeat this right now, but I think I need to. Okay. So anyhow, then you get B F squared equals B naught squared plus 2A. And there's my delta X again. And I put X's as subscripts to remind myself these are all X quantities. A is an X quantity too. Okay. Then I write the same equations on this side, except I use Y subscripts.
And what I mean there is like, it's important to have a model, but the system or actually properties, growth, characteristic. Maybe that 500 duration.
Now that you have those equations written down, you can adapt to the special case where the y acceleration is negative g and the x acceleration is zero. So I can write down okay. Now, in this case, I'm not given v naught x and I'm not given v naught y. I am given sufficient information to determine the angle. I'm given the slope. Well, that's a tangent of the angle, doing the inverse tangent of the slope. And if that's not completely obvious to you, your knowledge of right angle trigonometry, you need to think a lot more about your right angle trigonometry. That has to be automatic. And if you haven't done enough problems in right angle trigonometry, it's not going to be familiar to me. You got to focus on. Okay. As I do see, I mean, your right angle trigonometry looks pretty good, but you know, I saw on the homework, somebody did the arctangent of x over y. You got a ridiculous angle on one of their answers. Most of the problems solved correctly. So somebody knew what they were doing, just made a completely bonehead error, almost as bad as some of the ones you see me make. Okay. So don't think I'm calling you a bonehead when I'm not claiming to be other. Okay. Other than a bonehead, it was a bonehead error by somebody pretty smart. Smart people make bonehead errors. My nickname in high school, one of my best buddies was Bonehead. They thought it was funny to call him arguably smartest guy around, but there were a couple of other candidates. So they just like to call me Bonehead. Because we always play football. Yeah, Bonehead, look what you just did. Okay, well, anyhow. Huh?
I said, is that what they call me?
Yeah, the whole thing came out on the football field. And they called me Bonehead. Many called me Bonehead in class, and this one guy thought that was hilarious. So it just stuck. I didn't mind it a bit. Okay. Okay, anyhow. So if I use the word bonehead, please understand I do it with great respect. That was a bonehead error somebody made. I don't remember who. And I wouldn't call it a bonehead error if they hadn't done smart things. Okay. Okay, so AX is 0, AY is negative G. What else do you know? And this is where the trouble comes in on this problem. Okay. What else do you know? Delta Y equals negative 1 meter. That's all you've got. But that's 5 things. Okay. Now the problem is, normally if you've got 3 things over here, you can solve for T. If you're not already given T, if you're given T, it usually makes it pretty easy. Okay. And solving for T isn't hard if you know that the initial velocity is 0, right? The initial x velocity is 0. So that you know that, I'm sorry, your initial y velocity is 0, your initial x velocity is horizontal. I'll say it right. So there we have a conundrum because theta is unknown. I mean, theta is known, but v naught is unknown. So you're gonna have to combine what you get over here with what you get over here, and that gets pretty hairy. And we're not gonna do all that today. I'm gonna let you think about that, because it's gonna be, you're gonna need to be able to do that to analyze the lab. Some of the stuff we're gonna do in lab next time, okay? So there it is. This has the problem set up. Now, see how you can combine the pieces to make the jigsaw puzzle look sensible. Okay, make the pieces for. This is what I mean by design your solution. You're designing a solution here. There's more to designing it. What are you going to do with these things? Okay, well, among other things, X acceleration is 0, so that's going to be 0. That's going to be 0. And that's going to be 0. Okay. So this equation isn't telling you anything that this is. Okay. That's that right? This equation isn't telling you anything that this equation doesn't tell you. Okay. Now, this equation would allow that VFX equals the negative of V naught X, but that's ridiculous. You would discard that solution. Okay. Because clearly the thing keeps going in one direction. So this is sufficient. So you really don't need this equation. So you can kind of cross it out. It's redundant with what this equation is telling you. Now that still leaves you 3 equations. And of course, this equation tells you if you know V naught and T, how far it goes. So if you know how far it goes and you know V naught X, you can find T, or if you know how far it goes and you know T, you can find V naught X, and you know that perfectly well, because that's what you did in analyzing the lab turned in. Okay. Makes sense? Okay, you got a question? Okay, we have a good question. Keeping with the idea that we want to understand things as deeply as possible. That's a steel ball moving in this direction. It's also moving in this direction. But we assume that the air resistance in this direction, or even in this direction, is 0 because it's not moving that fast. If it was moving at the speed of a bullet, air resistance would be fairly significant and would slow the thing down. Not enough to save your life, but if it hits you, but slow the thing down. But we assume the only forces acting are, the only force acting on the projectile is gravity. Okay. So let's just kind of write that down. I'll write it in vector form. Assuming the y direction is vertical, acceleration is negative g times the j vector. In other words, make to the acceleration is p, it's in the negative y direction. That's all the acceleration, and this has no component in the x direction. Okay, so I could even emphasize that this is 0I minus gj. It's not necessary to write that out, but to just really make the point. Okay. And the reason again is you're moving through air. We assume you're working. We do the solution in the case of a vacuum. Okay. Now it's a more advanced experiment when we take all the air out of the room and do these things and compare this. Because everybody dies and that makes it really complicated. So we don't do that anymore. Okay. Used to be a mess trying to clean up the lab after, never mind. So anyhow, get it? All right. And in the y direction, then we can replace AY with negative G. Okay. So that becomes negative GT. And that becomes negative GT squared. That becomes negative G times delta Y. And your V naught Y would become V naught sine theta. So you just do these replacements. And the only number you really have, the only numbers you really have are the number for G and the number for delta Y. And then a number for sine theta and a number for cosine theta. Okay. Then you try to figure out how to solve it. It stumped me for a while when I took this course. Okay. I mean, I knew what to do, but I said, how in the world do you solve those equations? My algebra is pretty good, but, you know, as a freshman in a tough school, had to beat my head against the wall for a while. Got it set up, got the equations, didn't believe it. Convinced myself it was so, and said, how in the world am I going to solve it? Okay. And hopefully you'll get to the same point and you'll know how to solve it. You should have a lot more math in that head. Thanks. Okay. Okay. But it usually stumps most people. So don't feel bad if it stumps you, make it a good attempt at it. And I'm going to ask you to analyze that type of thing prior to lab. So we don't have to do the lab. I might even assign you to do this problem. But I might give you an angle instead of a slope or something. You can just make it easier. But if you got the slope, you got the angle. Okay. As soon as I find my document again, there it is. Okay. On number 32, the force of friction acts in the direction opposite motion. If an object is stationary, force of friction is equal and opposite to the sum of all other forces. I wouldn't bother writing this down. I'm going to give you the exact words. Okay, so you're not going to have time. I'm going to read them through fairly quickly. Okay. But I can demonstrate a little bit about what this means. So I'm actually not going to do what I said I was going to do. Okay. Okay. Friction is what stopped this thing. There might be a little uphill, a little downhill. So there might be a little bit of gravitational component. Actually, I should be recording this. So I'll get it together yet. Okay. Okay, I was recording where I thought I wasn't. So that happened. Anyhow, friction is what brought this to stop. Okay. Can you estimate what the frictional force is? 1,000. Okay, that took a little less than a second. That's about 60 centimeters. If you assume friction exerted a constant force, you can easily figure out what that force was. Okay, 60 centimeters, and let's say 3/4 of a second would be 80 centimeters per second average. So it started at 160 centimeters per second, stopped at 3/4 of a second. So you do 4/3 of 160, you get about 213 1/3. I think centimeters per second squared. Now, so if it's around 200 centimeters per second squared, what fraction of G is it? Well, G is 980 centimeters, about 1,000. So 200 out of 1,000 is 0.2, a number we already have on the board, but I didn't know that was going to happen. And this means something other than that. That tells me that the cofriction is that the weight is equal to the mass times the acceleration of gravity, right? The force exerted by friction is 2/10 of that. So we conclude that if what I did was correct here, force of friction on this domino is 2/10 of whatever its weight is. Now, spell that out more, but the book explains it too. Okay, so we have this thing called coefficient of friction. If I had a piece of rubber and tried to do that, well, it wouldn't slide, it would bounce. Okay, there'd be a lot of friction that would cause a thing to bounce, unevenness here and unevenness there. Okay. Another thing is, I don't have a ramp handy. But if I slide it along here, I'm not going to get the direction right. Yeah, there it goes. Anyhow, slide, and the camera wasn't on it when I slid it. And it's not going to be on it here, but what I did is I slid this domino, went about 60 centimeters, stopping at about 3/4 of a second. And based on that, we figured out what this thing called coefficient of friction would be for the domino. If I had a better tripod, which I do right in that bag there, I just got it the other day, so haven't had a chance to set it up. I could lower the camera and show you this. Can't do that today, but next time I'll be able to. Okay, depending on the surface, this is sliding across. Coefficient of friction can be greater or less. If we drop the temperature in this room to say 10 degrees Fahrenheit and dampen down the surface, we'll get ice and this thing will slide a lot better. Coefficient of friction will be a lot lower. I can figure out the coefficient of friction on this incline by the angle at which it starts to slide. Give it a little nudge so it keeps sliding. There it goes. Okay, well, whatever that angle is, the gravitational force component in the direction down the incline was G times, what is it? Gravity's in this direction. Your x-axis is in this direction so that you project this vector on here. So it projects at a right angle to this. And the angle you have down here is going to be equal to the angle you have here. You should know that. It's some, okay? And you will by the time we're done with exercise. This tells us that the friction was unable to restrain this thing when that angle became whatever it was, say 35 degrees or whatever. Okay. So we can calculate how much force was acting in the direction of the incline from gravity. And the fact that then this thing slid at more or less a constant velocity tells us that the net force on it was zero. Because net force is zero if it's not accelerated. Everywhere up to here, friction was exerting a greater and greater force because it was successfully opposing a greater and greater component of the gravitational force down the incline. So we can say that the frictional force is up to and including whatever the coefficient of friction is times the normal force, and we'll talk about it. That's just a little introduction to friction, which is related to my first comment. Okay, so keep this in mind. I'll be drawing pictures of it. But see if you can understand my words there, because the rest of it is pretty simple if you do. Okay. Somebody in number 36 used energy analysis to solve the problem, which was great. Would have been simpler, might not have been simpler. It's pretty simple. Number 36 is pretty simple if you just use energy. Okay, but you could also use equations of motion. Okay, You see what I mean by that? It's just an example of deciding which sledgehammer to hit the net with, which hammer is easier to wield. It's a toss-up. And you should be able to see it both ways. And that's my main point. Somebody did something boneheaded. No offense, I don't remember who it was, but multiplied 2.4 times 10 to the fourth by about 1,000 and got a multiple of 10 to the fourth. You multiply 10 to the fourth by 1,000, you get 10 to the seventh. Okay, so just, when you see that, just, let's not do that again. I'm sure knew better, just maybe doing that under pressure, whatever. It's easy to do that. And you see me do stuff like that all the time. So nothing to be ashamed of. Now, the one thing that somebody did that you really want to never do is you have a force in, you can see my hands. I mean, I can see them, but I can't see what's. If you have the X component of force and the Y component of force, you don't get the total force by adding, let's say this is 200 newtons and this is 500 newtons. You don't add 200 newtons to 500 newtons. They're not in the same direction. It's a vector. You get the resultant of those two vectors, and that gives you the magnitude of the angle. So that should be automatic. So whatever you do, don't ever add the magnitudes of two vectors that aren't parallel. Okay. And don't add the two magnitudes of parallel vectors if they're in opposite directions either. Okay. Make sure you express them according to their components and do the vectors. Okay. What about the climbing gymnast? All I say there is a net force equals mass times acceleration is gravitational force plus the applied force. Everybody pretty much got this, but a lot of people added the weight to whatever you get if you do F equals ma and got 698 newtons or something like that. Okay. And that's the way I solved it until I realized that you really want to set it up by just saying the net force is this force plus this force. Okay. The net force is the 198 newtons or whatever that you get from the acceleration. That equals the gravitational force plus the applied force. You solve for the applied force. And you want to do that because sometimes you really have to. On that problem, it's kind of obvious how to get the answer. But look at the way the textbook solves problems of that nature. They write the equation and then they solve it. They write an equation that says F net equals mass times acceleration. They write what F net consists of. They set that equal to the mass times acceleration and solve for whatever they don't know. Okay, they don't make an assumption that we can add this to that. Because for a problem that simple, yeah, you can probably get away with it. Pretty soon, you don't want to be in the habit of doing that. Okay. Now I did have a couple notes, number 64. A lot of problems got solved without using a free body diagram. Okay. At this stage, at the stage of chapter 5, you should be drawing free body diagrams. In chapter 6, which we're getting into, you absolutely must have the free body diagrams. Free body diagrams are how you understand forces, and it gets complicated. And if you don't have the free body diagrams, you're unlikely to ever sort it out by plugging numbers into formulas, okay? Somebody used 2g sine theta to find something related to the force of a crate on an incline. Somebody was using a formula that they didn't get from drawing a picture and working it out. That 2 doesn't belong there. Okay. Now I don't remember who did it. Everybody did some bonehead thing in the course on the homework. So I don't remember who did that. So don't hang your head in shame if you did. but that's an example of pulling out an equation without understanding the situation. That leads to later on using the AI to do something you don't understand and being unable to critically evaluate the result. Okay, so we'd want to get out of those habits. I mean, for your life, as it's going to be as an engineer, you really have to get out of those habits. But you should still be able to grab formulas and do stuff. I mean, there's understanding you can get that way too, but understand it as deeply as you can. And somebody on number 70, you got a runner starting out. And I can kind of gesture this if I can ever find Zoom again. I'm confused. You got a picture where the runner's on level, and here's the runner, and the runner is starting to push off, and there's a force arrow like this. Okay. Somebody drawing a free body diagram drew an arrow like this, where that force node was. Easy to get confused about that. The point is, that the free body diagram represents a force is acting on the object. That would be a force exerted by the object. This is a force exerted on the object being run. Okay. And incidentally, then this force has an upward component, which is going to be equal or a little greater than the runner's weight. And this component is the force that accelerates the runner. Okay. In the position the runner's in, he's not really in a position to speed up very fast. You know, if you start out, you're going to, the push is going to be at a much bigger angle, especially if you're in a race with blocks and you're going to push is going to be almost straight back. But that varies with the situation. If he's trying to run on ice, he better not have too much angle. If you're trying to run on ice, you're not showing one. Okay. Okay. Now I can't really spin this much because it's close to the board, but it will move in this direction. Now I've got a quarter sitting on there. Just I don't like to show off my wealth, but there's a quarter there. Okay. Anybody ever seen one of those? Okay, now it's going to spin. It's going to rotate a little bit, and that's going to stop. Is the quarter going to slide off? Yes or no? Quick. Nobody voted. Okay. Okay. What was the acceleration of that quarter? Well, we can say 1001, 1002, 1003, 1006, 1007, 1008. Okay, from there to there, I can see the angle pretty well. I say at about 1.3 radians in 8 seconds. Let's say 1.2 radians in 8 seconds. Okay, that would be an average of 1.8 radians per second. Started at rest, so that they say 1.8, 0.15. Okay, I know we got 1.8, but it's 0.15 radians per second average velocity. Change in velocity, well, it started from rest. Changing velocity within 0.3 radians per second. So just before it hit there, it was moving at about 0.3 radians per second. Okay, can you figure out how much centripetal acceleration? What is centripetal acceleration? What's your formula? Should be second nature to you already, because it appeared in some of the problems. But it'll be more second nature to you by the time you're done with chapter 6. Okay, so centripetal acceleration is v squared over r. Well, let's develop just a little of that. This. Yep, that one's. Painted on back, but this one has two sides, so. Okay, I paused. No, I didn't pause. Okay, centripetal acceleration. First place, there's your formula for centripetal acceleration. There's how you get centripetal force. You just multiply by the mass. Mass of a quarter, maybe around 12 grams. I don't remember. I've got a balance over there I could find out. Just say 10 grams. Okay. It doesn't matter. Whatever the mass of the quarter was, force of friction was the coefficient of friction, which we designate by the Greek letter mu, lowercase mu, times the weight, mg. Okay. Now there's kinetic friction and there's static friction. So I'm going to call this mu sub s for static friction. When, okay, static friction is limit. It's less than or equal to the coefficient of static friction times mg. In other words, coefficient of static friction times the weight. So something has a weight of 12 pounds and the coefficient of static friction is 0.4. 0.4 times 12 pounds is 4.8 pounds. It would take 4.8 pounds to break static friction. Okay. So if this exceeds this, then the thing's going to start to slide. So size of mass slides, at F net equals centripetal force minus mu k times mg. Notice I've got a k on mu where I had an s. Mu k means kinetic friction. Now, last time you tried to slide an appliance or a box or heavy object across the floor, you probably noticed that as soon as you exerted enough force to get the thing sliding, it accelerated. Okay? Imagine pushing a refrigerator across the floor, then the one that doesn't have wheels on it. you know, you push, and all of a sudden it lets loose and you can't move it just a centimeter. That makes sense? If not, go find something heavy, not too heavy, don't want to hurt yourself, and push it, and you'll find that it's not possible to push it just a millimeter. You're probably going to push at least a few inches. It's because you break the static friction and go to kinetic friction, which is less. This is less than this. So anytime this is greater than this, you have a non-zero net force. And that's instantly, as soon as you break free of the friction. And then you have to adapt, or the thing will keep speeding up. And that means you just have to exert less force once you got it moving. Maybe you throw your hip into it a little bit and move it on. You don't get, it doesn't accelerate to a house-destroying velocity immediately when you break friction. So you might even continue to speed it up gradually. You don't want it to stop because then you got to start it again. It stops back to static friction. Okay. Another important case is your tires. Your tires are in static friction, even though they're rolling. The point of your tire that's in contact with the road isn't moving relative to the road. What's happening is a new point's coming in contact with the road, and new points continue to come in contact with the road, unless your tires are spinning, which is why you don't hit the accelerator as hard on an icy surface or a wet surface as you might on a dry surface. Okay, coefficients of friction. You'll read about that in your text. Not sure my whole statement is visible there. It's a profound statement, so I'd like to have it off the screen. Okay, that makes sense? Okay, another situation, and let me check the time. We've got about 7 minutes. Okay. I wanted to demonstrate this, but I can't find my rubber band. We might have to break down, spend $1 on rubber bands before lab. But you've seen the situation where one of your problems, you have this traffic light, which looked a lot like a hooked weight suspended by 2 wires, right? I think that was the last problem with your homework. Maybe not. I should have read all the problems anyway. Well, whether or not, okay, so it's supposed to be a traffic light suspended by 2 wires. Of course, 2 wires would be suspended from a pole or cross piece or whatever. And you're given two angles, and you're given the mass. And you draw a free body diagram. Well, that free body diagram looks like this. You got the weight acting downward. Now, really, what you got is the weight's acting downward on this end of the wire, which stretches the wire a little bit and causes this end to want to pull toward this end. So the wire wants to compress so that whatever force it exerts down here is equal and opposite to the force it exerts up here. Okay, so the wire is pulling up on this mass, pulling down with an equal force, assuming that the mass of the wire isn't important. If there's enough mass in the wire, you want to take the mass of the wire into account, which the force up here would be a little greater than the force exerted down here. Okay, well, anyhow, you got mg. So right now we're ignoring the mass of the wire, and that's the force that's acting at this point. So really, we're looking at the forces that come together at this point. Then you have force F1 this angle is theta 1. And a force F2 to this angle is theta 2. Now, this is not a good representation of the relative forces. It's just giving you the direction of the forces. Why is this not a good representation? Because the horizontal component of this force, just project this down here, is about this big, right? And the horizontal component of this force is, project down here, it's about this big. So you don't have an equilibrium situation if the forces are actually represented by these arrows. Okay, I think your text tells you don't worry about how big the arrows are. I tell you, yeah, think about how big the arrows want to be, because it helps you validate your solution. So this arrow is going to have to be quite a bit longer because this angle is bigger than this one. So you have a component down here being more or less equal to the component here. So now, if you resolve these forces into X and Y components, which is what you always do, your X components are more or less equal and opposite. Okay? In order to make the X forces equal and opposite at this point, which is necessary for equilibrium, because if they aren't equal and opposite, since these are the only horizontal forces, you would have a non-zero net force, and there'd be an acceleration. What do you think about that? Because anyhow, you got F2 here and F1 here. Whatever these angles are, this is going to be F2 cosine theta 1. This would be like negative, that's F1. Negative F2 cosine theta 2. That makes it a little hard to read. In this direction, I don't want to draw the components right on top of each other, but you project over to the y-axis, and you get, this is your y component of F2. It'd be F2 sine theta 1. And you project this one over. And you get, don't leave myself room to label F2 here. Got F2 sine theta 2. Now, that should make sense to you because you've had problems with vectors where you get the horizontal components and add up the horizontal components and everything, okay? But just to remind you. In the X direction, you've got, and I know I'm off the screen here. In the X direction, you know you've got F1 cosine theta 1. In the Y direction, you've got F1 sine theta 1. And then you have F2 as negative F2 cosine theta 1 and F2 sine theta 1. And then you have negative mg. It's only in the Y direction. The sum of your X forces is written a little small. It's written F1 cosine theta 1 minus F2 cosine theta 2. In other words, just this and this. sum of your y forces is F1 sine theta 1 plus F2 sine theta 2 minus mg. Okay. Now, what else do you know about the x and y components? If this is an equilibrium situation, if this point is stationary, it's not accelerating. So its net force is 0 in both directions. If it's moving at constant velocity, maybe this is being carried along on a smooth rail on a railroad car, and it's moving at constant velocity. It's still equilibrium. It's not accelerating. Okay? Doesn't matter if it's moving or not, as long as it's not accelerating. That's an important point. So sum of the y forces has to be equal to 0. Sum of the x forces has to be equal to 0. You have two simultaneous equations here. And what's unknown? Well, if you're given theta 1 and theta 2 and the mass, which you are in the problems that you're going to see, then theta 1 and F1 and F2, the magnitudes of the forces, have to be adjusted so that these two are equal and opposite, and then whatever you get over here is what you get. It's two simultaneous equations, two unknowns, F1 and F2. Very easy to solve. If you remember how to solve two equations and two unknowns, and you've had linear algebra, so if you haven't, you really need to beat your head against the wall a little bit and review that. Okay? Does that make sense? That's a typical kind of problem that you encounter. The rule is equilibrium is equivalent to acceleration equals 0, is equivalent to the sum of the x forces equals the sum of the y forces equals 0. Okay? So that's a formula, if you like, but the formula should make good sense to you if you think about what you've seen. Maybe it makes good sense to you already, even though I explained it rather quickly. Okay? Make sense of it. Your book will help you. Video will help you if you got to re-look at it. Can you download a transcript? You can get a transcript of these videos. Can you open it and copy it? I can. I'm going to see if I can open and copy my own transcripts, just anonymously on YouTube, because that can be helpful, even though they're unedited. You can still scan, read a couple of lines and see what I'm talking about. And although that's not it, that's close to the end. Oh, there it is. If my words are any good to you, if somebody else's words are good to you, use them. But above all, understand it as thoroughly and deeply as you can. And we're about 4 minutes over time, for which I apologize.